The situations we had until now are if we want to have sender anonymity, it's really expensive. Why? In the ring network, providing a kind of ring, a physical structure, is expensive, and it has the property that if you have a ring of, let's say, 1,000 stations, and you have some fixed bandwidth within the ring, then it's pretty clear, on average, each station can only send 1 in 1,000 parts of the bandwidth, right? Because 1,000 stations share the bandwidth of the ring. So each gets only a fraction, 1 part within 1,000 parts, 1 promille. Same argument with the superposed sending. Maybe I should go back to that slide. If station 1 wants to send a message, as is depicted here, all other stations have to send a message as well. In here, they have to send the neutral element. And again, all the stations share the bandwidth of the network. In this example, if you have 3 stations, each one can only on average use 1/3 of the bandwidth. If it would be 1,000,000 station, this would mean each station only could use 1 of 1,000,000 messages for sending, right? Which means the larger the network gets, the smaller the fraction each station may use for sending. Doesn't sound well. Because usually, if we build networks which scale, it's a very bad idea if our network gets bigger, that what we might use within the network gets smaller. I'm pretty sure nobody would enjoy that. But this, of course, is a consequence if all senders share the same fixed channel as in the ring network at the physical layer, or here in the DC network at the logical layer, some layer where we say we have this kind of additive channel. So until now, no anonymity systems which are deployed at a large scale use any of those techniques. And if you are starting to implement the DC network, the DC plus network in particular, for gaining some resistance to data retention, then we don't aim, I wouldn't hope that we will be able to run networks of millions of users within a particular DC network. I would be very happy if the outcome is it can be, let's say, 1,000 users. Even 100 users, I would say, is a good result. Now let's start with the mixes And the mixes are a technique which scales much better, which is one of the reasons why mixes are implemented on a large scale. They are usable for sending email, for browsing the web. They are usable for different purposes. They are first invented in 1981 by David Chaum. And David Chaum invented them for electronic mail. So first I will describe everything in a kind of framework for sending messages. And later on I will discuss whether mixes can as well be used for switching channels. So what's the idea? The idea is we have dedicated network stations called mixes, which receive messages, batch them, they store them. For cryptographic reasons, they will discard repeats, and then they forward the messages to maybe a next mix, mix 2 here. And this mix again batches, that is, the mix awaits enough messages, again discards repeats, and again changes somehow the appearance of messages and outputs them again. So if you look globally, and in this drawing we pretend we can look into the messages, which in reality we couldn't. So if you look into this message, you see, hey, this gets that, and this message then later on gets this. So this message makes it that way. If you only look at the outer appearance of the messages, you wouldn't have a clue whether this message here gets this, that, or that. And again, nobody would have a clue whether to this message the input message was this, this, or this. What is clear is that this mix 1 knows which of his input messages correspond to his output messages. And it's pretty clear that mix 2 knows which of his input messages corresponds to his output messages. But as long as mix 1 and 2 don't cooperate, nobody knows which of the original inputs corresponds to the final outputs. It's pretty clear if mix 1 and 2 cooperate, if they pool their information, if they share their information, then they can determine this message was transformed to that message. This is something mix 1 knows. And this message then is transformed to that message. This is something mix 2 knows. So if they pool their information, they can trace the message from here over there to there. But assume we are not using 2 mixes, but 10, or maybe even hundreds of them. Let's assume those mixes are in different countries, are operated by different operators, where we choose the operators such that to minimize the probability that they cooperate in a secret fashion against their users, then it gets really very unlikely that all the mixes cooperate to trace users. So maybe one of the mixes is operated by the German Ministry of the Interior. The next mix is operated by the Italian mafia. So I would usually assume that the German Ministry of the Interior and the mafia don't cooperate. You never can be sure, but I would say it's relatively unlikely. And then let's assume we take one mix operated by the Roman Catholic Church. Okay, now it's cooperation with the mafia. Okay, now it gets difficult. As some people might see it, other people would say, no, never ever the Roman Catholic Church would cooperate with anybody. But, okay. So you see, if we take very different operators of mixes, it gets unlikely that they cooperate against their users. Of course, if the German Ministry of the Interior run Microsoft software operating system, if the mafia runs Microsoft software, maybe the same. And if the Roman Catholic Church runs Microsoft software, then the interesting question is, hey, would Bill Gates be in a position to trace the messages? And if Bill Gates would be able to trace the messages, would then the American government be able to trace the messages? Because maybe they have a particular relationship to Microsoft. The answer is, we don't know. Of course, if you ask Microsoft, they will tell you, we never ever will particularly cooperate with the American government. But probably it's pretty clear that even if they would cooperate with the American government completely, of course in public they would have to say, we never do. So it's not really useful information you get by asking Microsoft. And of course the same story would be true if I would replace Microsoft by Apple. The only thing which makes Microsoft special is that Microsoft on the private laptops and desktop machines is the market leader, and Apple isn't. How to argue about Linux? You might argue Linux is open source, everybody could inspect all the code. So I hope whenever you boot your machine, you inspect the code. Okay, history tells us that even within Linux, it has lasted for years before severe flaws have been detected. So if within a project like Linux, you would have programmers with good reputation which would intend to build in a Trojan horse, I would argue probably it's doable. And it will take months, if not years, before it will be detected. So what to do? Make sure this mix runs maybe Linux. This runs Mac OS. And the third one runs System 7 or something like that from Microsoft, right? Then hopefully Linux, Apple and Microsoft don't use common software engineering tools. If they use a common compiler, I explained to you what a transitive Trojan horse is, you could have a problem. So what you see, mixes really should be independent. By the way, is this really new? I would argue not really. Because, for example, if you implement the DC network and all the participating user stations run Windows, they all share the same Trojan horse, then it's pretty clear what maybe the US government could do. So usually when we are talking now about anonymous communication, we assume that not all the operating systems are working against the user base. If they do, zero chance. Okay, so let's assume that. How do we do it cryptographically? Here in this picture, I just gave you the feeling that messages are somehow put into boxes of different forms. And indeed, you could do so. For example, if you would like to order physical goods from Amazon, you could ask Amazon to ship your goods using, for example, DHL to some place of another delivery company, repackage the goods, and then send it to you. Of course, everybody would argue that, hey, if it's about energy consumption, this isn't a good idea. With respect to privacy, it might be a good idea. And this is mainly the same we do with mixes. Messages are not sent the direct way, but they are routed through additional stations called mixes and change their appearance there. And of course, it's not repackaging them physically, but do it cryptographically. And this is how it might be done. Mix 1 chooses a key pair, a decryption key D1 and a ciphering key C1. And the main equation we know is if you first encrypt using C1, you later on decrypt using D1, then it cancels. And what we encrypt here is a random number Z, Zufallszahl in German, and the message M. And of course, if you first encrypt and then decrypt, you get it again. What is output from the mix is the message only, not the random number Z. Why? Because if you would output Z as well, if you would output all you get by decryption, then you could just take the output, each single output, use the public key of the mix, and encrypt it. And then you would get one of the inputs. Therefore, it's essential that at least some part of the message is never output by the mix, just to prevent that someone takes the output units and encrypts them again and compares with the input units. The same happens here with mix 2. It has a key to cipher, a key to decipher, and again we have probabilistic encryption by means of this random number Z, and it's only the message which is output. So in this simple scheme, how are messages be prepared for processing? You take the message, which shall make it to the final recipient. You encrypt it probabilistically with the public key of the last mix. And then the result you encrypt again probabilistically with the public key of the mix before. And in this case of two mixes, this is the end of the story. And then on its way through the mixes, this message, first in mix 1, is decrypted, being the inverse to the last encryption here, and it gets this message. And then it's decrypted with the inverse of the first ciphering key, and then it gets this message. Okay? In this scheme, which is the basis of the electronic mail system David Chaum described, for each message, you need an asymmetric cryptographic operation. This is not really a problem if we are talking about email. An email may well take a few minutes to reach its final destination. And some people even would argue it may well take a few hours until it's reaching its final destination. By the way, many of you, including me, in the meantime, are using email mainly as instant messaging. So we assume that an email I send is with my partner a few seconds later. But this is not the original definition of service for email. Email means arrives within a day or two. Or let's be a little bit more optimistic, arrives within an hour or two. If we would talk about browsing the web, or if you would talk about telephony, getting the message with a delay of an hour or two probably wouldn't be much fun. If you ask for a web page, and after an hour or two you get it, then probably you are using GPRS, and you have a web page which is heavily loaded with high-resolution computer graphics you never need on your screen. So this is the feeling you get. And when I first experienced that in my life, I really got upset. So we need a better strategy for those applications. Or if you're talking about telephony, what is an acceptable delay? Usually telephony means two people interact, right? How much delay couldn't you stand? Anything larger than half a second or so means that both will interrupt each other from time to time. They will appear to be very unpolite because they will interrupt very brutally. But all what happened is you have the delay. So both start talking, and only after half a second they notice, oh, shit, we started roughly at the same time. Let's do it again. So you have a common feeling what is a good pause. So maybe you wait a second just to be polite, and then you start again. And your partner, who has roughly the same feeling about timing, will do the same. So shit, second collision. So, okay. And now you either would need a kind of protocol for telephony where you would say over explicitly, or you need a channel with a much smaller delay. So what could we do for mixes? We could try to use the scheme I just described, which works fine for electronic mail, for channel setup, for exchanging keys, maybe of a symmetric system. And then we use the symmetric cryptographic system for the real communication. This means a mix does not incur delay for an asymmetric encryption system, but it only incurs delay for a symmetric one. And for a symmetric one may mean, if you are talking about the one-time pad or the pseudo one-time pad, a mix only incurs delay of 1 bit. And now it gets much more practical. So this is the idea that we take the asymmetrically encrypted and decrypted messages for connection setup, or in the limiting case for channel setup, and then have much shorter delay within the connection or within the channel to enable services we couldn't enable if we just would stick to message passing, or more precisely, the passing of messages which are unrelated. Doing a little bit more privacy discussion. If you have these messages, and if you look here and here, all these messages look pretty unrelated. If in the next time frame, again, the public keys of the mixes are used, the messages of the next time frame look completely unrelated. The mixes have no need to know whether messages are related, because they just take their secret key. They just have one secret key, and they decrypt it. That's it. No need for mixes to know any relationship between messages. This is surely different if you are talking about connection setup or channel switching. Because if this line here means everything coming in here is decrypted with a symmetric key, with a particular symmetric key, which is a different key than this key which is used to decrypt here, which is a different key than this key which decrypts here, then surely if you did establish connections which each have a different symmetric key, mixes have to know if you have incoming bit streams or incoming packets, to which connection, to which symmetric key do these packets, streams, whatever you have, belong. So here, everything is simple. Each packet, each message is processed completely independently from anything else at the cryptographic level. Here, some relationships are established. All messages which are transmitted within one connection belong together. And mixes have to know that they belong together because they have to use the same symmetric key, which is linking all those messages. Linking those messages, of course, isn't a problem if those messages are linked anyway. But for some services, it may be some kind of additional linking, and then we should do some evaluation whether it's worth it or not. Okay, so far, the high-level principles. So what are basic functions of a mix? First, a mix gets input messages. Okay. Next, the mix is going to discard repeats. How to do that? To do that, the mix needs somehow a database of all input messages which were or will be re-encrypted using the same key. So if you want to discard repeats, you have to remember what came in before. Why do we have to discard repeats? If I put in the same bit string here twice, I will get out the same bit string twice. Because decryption is deterministic. Even if encryption is probabilistic, and in this sense is indeterministic, decryption is deterministic. And therefore, if we wouldn't discard repeats, it would mean same input, same output. How could you use that to attack mixes? Okay, if you are interested in some message, you just make sure it's input twice. And then you look which bit pattern will repeat twice at the output. Now you know what the mix made out of the message you are interested in. And if this doesn't give a unique result, then you put it in 3 times or 4 times or at certain different time intervals. Okay. So, because decryption is deterministic, we have to discard repeats as long as the key for decryption is the same. Which, by the way, then means that mixes mainly are not crypto devices, but that mixes mainly are huge database systems because they have to store lots of messages. Then a mix has to buffer the current input batch. It has just to buffer all the messages which are not repeats for some time, just to make sure enough messages made it to the mix. If possible, the mix should check whether there are sufficiently many messages from sufficiently many senders. Of course, if you're talking about anonymity, if all those messages all come from the same sender, it doesn't generate anonymity. So it's not only that you have enough messages, you should have enough messages from many different senders. By the way, this is of course something which is not really easy to enforce. Because how do you make sure on the internet that two messages are not from the same sender? If we would have a public key infrastructure, the German government is just trying to get it using the next generation of passports. If we would have a public key infrastructure, we could say everybody is going to sign all the messages. And everybody has only one public key in his passport. Then you could use that to make sure that two messages originated with different senders. As long as you haven't a PKI, how should you know that it's from different senders? So hopefully we have sufficiently many messages from sufficiently many senders. What do we do if we haven't enough messages? Two strategies. Wait until more messages arrive. Or insert dummy traffic, generate messages, generate dummy traffic. Then re-encrypt the messages. And in the examples we just had, it mainly meant decrypt messages. For some other schemes, we'll come across them, it might mean encrypt messages. But here, for the simple examples we just had, it means decrypt messages. Then, finally, the mix should change the order of the message. So no first in, first out. Otherwise, it wouldn't be useless to do cryptographic stuff on the net, on the messages. And then you output messages. This is what a mix does. And in one of the exercises, I'm asking you the question, is then the flow of operations uniquely determined, or could you start with other operations? And I think this kind of flow of events mainly is a canonical implementation. What does this mean with respect to delay in each mix? It means discard repeats means you do a lookup in your database. Usually this means at least one access to your hard drive, which roughly means 10 milliseconds. Okay, in older times, or if you have a very slow hard drive, maybe it's 50 milliseconds. Sufficiently many messages from sufficiently many senders. In the fast variant, we are just going to ignore the problem. In the most expensive version, you are checking a digital signature, and maybe even you are checking the corresponding public key certificate. So I took twice the time of an asymmetric encryption, so 100 milliseconds for digital signatures. Then we encrypt or decrypt. If it's special hardware, maybe it's fast, maybe it's 1 millisecond. If it's software, again 100 milliseconds. Some reordering, maybe it's very fast, some nanoseconds or a few microseconds. And if you add it up, and if I did that correctly, it mainly means in the fast variant, you end up with a time which is given by your hard drive. And if we are using costly asymmetric operations, then it's mainly given by the time needed for doing the encryption, decryption, testing of signatures. So you see, if it's 11 milliseconds, we could afford a few mixes and still do telephony. If it's a quarter of a second, then having, let's say, 2 or 3 mixes is not a good idea, at least for a normal conversation. What properties of mixes we would like to have? Mixes should be designed independently. So no common design problems. They should be produced independently. The code should be distributed accordingly. They should be operated independently. So one by the German Ministry of the Interior, one by the Mafia, and one by the Roman Catholic Church, in the example I used in the beginning. And of course, they should be maintained independently. So one by the German Ministry of the Interior. I'm not sure whether they have much experience in software maintenance. One by the Mafia. Probably they know better what they do. And one by the Roman Catholic Church. And again, I'm a little bit in doubt whether they have real experience in software maintenance. Okay. What might be a very bad idea if all the 3 of them hire a consultant, because maybe the same consultant to all of them. If I would be the National Security Agency, I would offer consultancy services to all mix operators worldwide, right? You see the motivation? Messages passing through mixes should be of the same length. Because if they are of different length, then it's easy to trace messages by their length. And those messages of the same length should be buffered, re-encrypted, and the order should be changed in a batch-wise fashion. That is, you take several messages together, maybe a few or some hundreds or maybe even some tens of thousands. You buffer them, you re-encrypt them, and you change the order. Each message should be processed only once. And this has to be true first inside each batch, but, and this makes it more difficult, it also should be true between the different batches. It has to be enforced as long as you are using the same key. Okay, if you want to get rid of the database, what do? After each batch, you're changing your key, right? Then you don't need a database to check between different batches whether the message already has been processed. But key exchange also incurs some expenses. And if you want to have something like a return address, that is an address which can be used, which surely then has to do something with the keys of the mixes. So the return address is only valid as long as the keys of the mixes stay the same. So if you are now changing the keys after each batch, then it makes return addresses really a problem. So it's not really a very easy solution what to do to ensure that each message is only processed once. Next, can we use symmetric encryption? In the picture I showed to you, I only had asymmetric encryption. And in the general case, for mixes, you really need asymmetric encryption, at least to start with. Maybe you use asymmetric encryption to bootstrap symmetric encryption. That is mainly, you do something which we called hybrid encryption last year, right? So the question here is, can we use symmetric encryption from the very start? And the answer is, for some of the mixes, yes, but not for all of them. We may do so for the first mix, because usually in our attacker model, okay, I should talk a little bit about attacker models. Usually we assume that, like in the DC network, in the mix network, all lines are tapped. That is, everybody knows which messages make it to the first mix. Even the mix may know from where those messages come, because maybe the mix is using an IP protocol, so each of those messages has an IP sender's address. Again, those messages are transmitted. Let's assume all those messages are tapped. And finally, those messages are transmitted. Let's assume all those messages are tapped. So the last mix knows to which IP address, for example, he's sending. And now the first mix and the last mix, and in this picture, regrettably, we have no middle mix. So the first mix knows where messages come from. So he knows the sender. So he could exchange with the sender a symmetric key, which then he might use. The last mix might know the recipient, though he might exchange with the recipient a symmetric key he might use to encrypt the message. But a middle mix, let's imagine we had one, a middle mix should neither know where the message originally came from, nor should he know where the message finally goes to. And therefore, a middle mix would have no information, or should have no information, which symmetric key to use. And therefore, middle mixes mainly need an asymmetric encryption system to bootstrap, if symmetric keys are to be used, to bootstrap it in the way hybrid encryption works. So symmetric encryption exclusively can be used only with respect to the first and last mix. For the middle mixes, maybe you use hybrid encryption, but in any case, you have to use somehow asymmetric encryption. So what is our aim? What do we want to achieve? And first, I'm going to formulate it without any dummy traffic, because our aim is clearer if we keep the mix functionality pure and don't intermingle it with dummy traffic. So what we would like to have is that the communication relationship can only be revealed by either all other senders and recipients working together. So let's assume you two are communicating to each other, and all others do communicate as well to each other. Now, except you two, we all agree that we want to trace who communicates to whom. So we take one message after each other and just figure out who did send it, who did receive it. And if we then come across messages where neither of us says, I'm the sender or I'm the receiver, and you are the only two guys who are left open and left over, then it's pretty clear you exchanged the message. So you know each other, you have some kind of communication relationships. So, and this of course is now a statement which is a very fundamental statement. If you have a set of users communicating and everybody's cooperating except two, then these two probably haven't any privacy. Can you improve that? Yes, by dummy traffic. Of course, if we introduce dummy traffic, that there's some message nobody of the rest is involved in, it could mean you have some kind of relationship or you're just sending dummy traffic to somewhere. But if you ignore dummy traffic, if all the rest works against two people, then they have not really privacy with respect whether they communicate yes or no. Okay. And the second possibility is how to trace people, that all mixes work together, and in particular all mixes which the message passed. So please remember, even if you use mixes, there are ways to trace who is going to send to whom. Two possibilities, either all mixes. This is what is usually discussed. And this usually is done if you are talking about data retention with respect to mixes. If each mix has to retain data, which input message made it to which output message, what the relationship is, and has to hand that information over to law enforcement, then it's pretty clear how to trace messages. Of course, the problem is if you keep that information and if you can pass it to law enforcement easily, then probably if someone shows up in your office and tells you, hey, this is a firearm, please could you tell me the information, then probably it would be relatively straightforward and easy to hand over that information to non-law enforcement agencies as well. Or if some computer which stored that information ever gets hacked, you might have the same problem. But keep in mind, even if the mixes never ever will work together to trace people, if enough other people work together, if enough of the users work together, it will have the same effect. We had in the DC network the discussion, if I get to see a message which is threatening someone. And we had a discussion over the break whether such a message should be traced and could be traced, because maybe not everybody agrees whether it's threatening or not. Here, pretty much the same. Even if the mixes don't cooperate, if all but 2 users cooperate, then mainly the game is over. Okay, let's assume these are the aims. Can we draw some conclusions about what might be possible, what might not be possible, and how an implementation would look like? One conclusion is a conclusion about the re-encryption business. And the conclusion is we will never have a decryption directly after an encryption. Why? For the decryption of the encryption, we would need the corresponding key. And then, before and after, the message would be the same. So this encryption, decryption would be pretty useless. So this is one rule we might keep in mind when designing re-encryption schemes. And the second conclusion is that if we want to have maximal protection, then all the mixes should be passed through simultaneously. And if we require that all the mixes are passed through simultaneously by all the messages, then it follows that they are passed through in the same order. Here in the 2 mixes in this example, probably you hadn't the feeling that I'm talking about routing. And in effect, if you take implementations of mixes, for example, Tor, you have an awful lot of flexibility which kind of routing to use. And many people have the feeling, hey, if each station does routing independently of all the other stations, this gives many more possibilities. And intuitively, many people believe more possibilities means more protection. But this conclusion tells us if we are aiming at a strong attacker, if you are aiming at an attacker who controls all mixes which are passed, but one, then we can conclude that all mixes should be passed through simultaneously. I will argue that in a minute. And since this is true, we can therefore argue that mixes have to be passed in the same order, which means that against strong attackers, free routing through mixes is a splendid, stupid idea, which is one of the disputes between my research group and the Tor group, where I say Tor is, I would say, ill-designed because it gives flexibility in a situation where against strong attacker there should not be any flexibility. It should be used for the same mixes. But of course, in a peer-to-peer network setting, it's really hard to fix something. So we in the Unknown project decided to have a fixed sequence of mixes in the so-called mix cascade. And of course, it's not peer-to-peer, it's more server-based. Okay, so maybe I should next argue, why is it important that mixes are passed through simultaneously? And this is done through this drawing. Let's assume mix I is the only mix which is a good one. All the other mixes are compromised by the attacker, which is the usual setting if we are talking about a strong attacker. A strong attacker might compromise all mixes but one. So mix I is a good one. Now let's assume that not all messages pass through mixes in the same order. So with respect to the good mix, we have some blue messages and some red messages, assuming that the blue messages pass, for example, earlier, and the red messages pass later. So they don't pass at the same time. Then, because all the other messages are bad, we could, of course, trace back these input blue messages to their original senders. And of course, the output blue messages we could trace to their final recipients. And then we would know these three senders communicate with these three recipients. The same we could do with respect to the red messages. We could take the red input messages of the good mix, we could go back, and we could take the output messages of the good mix, the red output messages of the good mix, and we could go forward. And then we could know, okay, from these three senders, the following three recipients get a message. And what is information gain by that those three messages pass through the good mix at a different time interval than these three? The information gain is, in an optimal system, we would know, okay, there are 6 senders, and any of the 6 senders could send to any of the 6 recipients. And this gain here tells us there are 3 senders where we know they are sending to 3 recipients. And there are other 3 senders which send to other 3 recipients, which gives us more information about who is sending to whom. So in a setting where only this mix is a good one, this gives additional information, which means that if you want to have maximal protection against a strong attacker, all messages have to pass through all mixes in the same order. Until now, with mixes, I didn't mention sender anonymity and recipient anonymity. You remember, we had sender anonymity for the DC network. Recipient anonymity was provided by broadcast. In the ring network, we had recipient anonymity by the broadcast nature of the ring. We had sender anonymity by not being able to trace all the lines. Now we should discuss which use of encryption supports what kind of anonymity. And the basic scheme I started with is a sender anonymity scheme. That is, the sender is going to encrypt many, many times, according to the number of mixes, the message. Then it sends the message to the first mix. This mix decrypts, sends it further to the next mix. The next mix decrypts, sends it further to the next mix, decrypts, and so on and so forth. So I'm using here a graphical notation where downwards means encryption, horizontally means transfer, and upwards means decryption. So why is this a sender anonymity scheme? The recipient who finally gets the messages, or the message, even if it works together with some of the mixes, but not all of them, has no way to determine the original sender. Because for one of the mixes, he doesn't know which input of the mixes working with him corresponds to which output of the mixes cooperating with him. Why is this scheme not a recipient anonymity scheme? Because the sender, who does all the encryptions one by one, of course knows all the intermediate states of the message. So here, the sender knows the output of the last mix. Here, the sender knows the output of the mix before, and so on and so forth. That is, the sender, by keeping those intermediate values of the message, the sender could trace the message on its way to the recipient. And therefore, it's a sender anonymity scheme. The sender knows, but the recipient doesn't. I call this scheme a direct re-encryption scheme for sender anonymity because the asymmetric keys are applied to the whole message. And an indirect scheme is a kind of hybrid encryption scheme where I'm using the public key of a mix to encrypt a symmetric key. And I do that, if I like, for all the mixes. So each mix first does a decryption with his secret asymmetric key. Then he gets a symmetric key, which is in its use much more efficient. And then the symmetric key is used for, in this case, decrypting the whole message. Then again, it's forwarded to the next mix. This next mix uses its secret decryption key to decrypt a symmetric key. The symmetric key is used to decrypt the whole message, which then is passed to the next mix, and so on and so forth. And here, I did give you the coding scheme as a set of recursive equations. So this is sender anonymity in a direct way and in an indirect way. And now it's a quite natural question to ask, could we do recipient anonymity? And the answer is yes, we can. Here in recipient anonymity, we would require that the recipient does an encryption again and again and again and again. Then somehow this kind of return address is transferred. I call that an unobservable transfer, is transferred to the sender. And then the sender gets a symmetric key. So it's an indirect scheme as well. And this symmetric key is used to encrypt the answer, the message back. The next mix, by using its decryption key D1, gets another symmetric key. And this symmetric key is used to once more encrypt the message. So with a scheme for recipient anonymity, a message has now two parts. The leading part is decrypted. And the answer is encrypted. So finally, the recipient gets back some part which tells him, okay, this is a set of symmetric keys. And then he uses those set of symmetric keys to decrypt in the appropriate sequence of the keys the message back. So, and again, you might write that in a set of recursive equations. I call this the message header, and I call this the message content. And the sender, the recipient forms the header, just starting with a kind of value he will get back. And then he's going to encrypt it for this mix, 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 sends it, and then the sender will put it on its path through the mixes in this direction. And in addition, the sender will put the message content towards its way, and each mix will encrypt the message content. So in the end, the message header is completely decrypted when it returns, and the message content is maximally encrypted when it returns. So the recipient has to decrypt it in the appropriate fashion. So do you have questions?
How can you make the transfer unobservable, the initial transfer?
For example, I could use a sender anonymity scheme from here to there. Unobservable here means it should be unobservable from the sender and maybe the mixes. So a scheme from here to there could just be a sender anonymity scheme used by R to send something to S. Okay. Further questions? What is the next question? What is the next problem to be solved? Yes, sure. How do we do it? In some sense, we just put both schemes together. So if you look here, this seems to be mainly a sender anonymity scheme because we only have decryption, and we do it for the message content as well, decryption all the time. And this part is the recipient anonymity scheme, where we have decryption for the message header, and where we have encryption for the message body, for the message content. We have a kind of third party which may be used to start the communication, because how do you start communication if you don't know to whom you want to communicate? And here you need some kind of third party which at least tells you something about your communication partner. Because if you have no clue to whom you want to communicate, then I would argue communication is nonsense. But if you have some kind of service, so maybe you have a third party who says, okay, maybe it's a kind of dating service. So you are looking for a nice woman or a nice boy or whatever you're looking for, I don't know. Maybe there's some service offer. Hey, I can give you a possibility to contact some women or boys which are interested in some kind of dating. In the beginning, you don't know who you are contacting. So first you communicate, and only if you have the feeling you are really interested in, then you tell the other person who you really are or how to really meet. So this is just one use. Maybe there are better uses than anonymous or pseudonymous online dating. So what would we do? If you start here, you would query this service with a kind of sender anonymity scheme, and then you get some information how to contact that person. You would pick up it here using some recipient anonymity scheme, and this could again be initiated using some kind of sender anonymity scheme, and then it would work. So going back, mainly it means both schemes are used. You have here some interfaces where you couple the communication. And for setup, you need a third party, because otherwise you have no clue whom to contact and how. And this party gets some information by R, maybe by S. They want to participate. Then later on, R and S have to take up the information of the other party, and then it might start. Okay, so see you next week.